Remind me of your name. Remind me. Yeah. Is what? Yeah. Okay. All right. Good deal. Now, okay, why does this say no signal? That's just scary. This morning it said no signal because I forgot to plug in the thing. So let's try here. Anyone know anything about these things? What's that? This happened next door, and I figured out the buttons that made it work. Let's see if I can figure out any here that make it work. Ha! That did. Yes. Okay, we got it. Whew. Okay. We'll go. Okay. Now, my question to you before I do any more, is this where we left off last time? No. Had we gotten to this slide? No. We had not? What's that? Slide 5? Is that far up? Let's just go. Have we done that?
Okay, right here. Okay.
Had we done that? What's that?
The last one to that last chart. I went to the last chart that we were going into.
Okay, that was the one we were going to do.
Yeah.
Okay. So is that okay to start today? Okay. Then let me go from current slide. All right. Now, before we do anything else, let me tell you this. Sorry it took so long. Last week I had requested, because they had offered, from the guys from Cengage, people from Cengage had said, let us set up your course for you if you blah, blah, blah. So I requested late Friday afternoon. I mean, I didn't even see it until sometime over the weekend when I happened to be checking email. Late Friday afternoon, the guy I had sent it to said, could you give me a call on Monday morning regarding the setting up of your courses? I thought, I was expecting them to be set up by now. So I called him Monday morning, and he sort of new at the job, and he had all these questions, so he got it. So sometime yesterday afternoon, he finally got them done. So here is your class code, they call it, so you can access your ebook, you can access WebAssign, you can do anything you need to do. Here it is. Let me get my pen adjusted.
So you just said WebAssign. We have WebAssign assignments.
I don't do any assignments on them, but he's put some problems out there. I don't know how many. He did it. I give problems from the book. Okay, but you can do them if you need extra ones to work on, and I think WebAssign does have pretty good tutorial help. So use it. You know, you paid for it. You got it, Toyota. Yeah, okay, whatever. Okay, here's a code. LAWSON, Lawson, .AL, space, 1139, space, 2952. Okay? That should get you access to everything in the course. Okay? Lawson.al space 1139 space 2952. Okay? Sorry that it took me this long to get it, but they had a delay last week, over the weekend, and they did get it to me yesterday. I'm going to send out notification via Blackboard, so anyone who's not here should be able to see it. hear this as well. Okay. Also, I made progress on syllabus and that kind of stuff, but not far enough to get it on Blackboard yet. So nothing's on Blackboard yet that I can think of for this course. I'm going to try to work on it some today. I don't have but a little bit of office hours today. I have some time tonight, I hope, and I'll try to work on it then. Tomorrow afternoon I have a little bit of time, office hours, and then the same thing Thursday as today. And then finally on Friday, I hope to have a chunk of time to catch up anything I haven't made by then. Okay? But at least I made a little progress here. All right. This, I think, is where we left off last time. I think we had done most of these things, but these are good illustrations of it. Before we get started, any questions from anything we've done so far? Okay? And as I was just saying, the guy who set this up, I haven't looked at what he did, but I asked him to put just a few sample exercises out there. I don't know if he did one or two, if he did a whole bunch. I don't know what he did. They're on WebAssign, and you certainly can go and use that supplementary. WebAssign has really good, I understand, tutorial help, so use that as well. Any resources that are there, it's open to you to use them. Okay, this book, to me, has all the resources you need because this author has 3 different sites out there: LarsonPrecalculus.com, CalcChat.com, and CalcView.com. And those have tutorial helps and explanations and things. This is a good author. I don't like the company that much, but this is a good author. All right, so here is illustrations of radian measures. And it's stuff we've already done. We started the other way. It's going sort of backwards. So let's go back to the way we did. If you had a circle, okay, what is the arc length of a complete circle? 2 pi r, okay? Now, where r is the radius. So the ratio of the arc length to the radius would be 2 pi r over r, right? If this is, use the wrong pen here, if the arc length here is S is equal to 2 pi r, and r is your radius, then the theta, your radian measure, is arc length divided by radius, which would be 2 pi r divided by r, and that would be 2 pi. And that's why the radian measure of a complete circle is 2 pi. Okay? So if the whole circle is 2 pi, what's half a circle? Pi. What's a quarter of a circle? Pi over 2. What's a quarter of that? I mean, a half of that. That's pi over 4. Okay? So let's go back to your pi here, and now rather than split that in half, split it in thirds. So that would be pi thirds right there. Now remember, pi thirds, if you think in terms of degrees, is 60 degrees. And remember, 1 radian was about 57 or something. So this is a little bit more than 1 radian, just for what is a radian. Okay? Well, you think about this. What is pi? No, pi. The number pi. What is it?
Oh, 3.1416,
3.1416, blah, 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 blah. Okay? So, if you have 3.1416 divided by 3, that's just a little bit more than 1. 1.05 something or other. Just a little bit more than 1.
Well, you just said 3.146.
What's that?
Okay to round it up to 3.15?
Yeah, it's actually 3.14159, blah, 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 blah. You just keep on going. Irrational number never produces a pattern, never repeats itself, just keeps on trucking. Okay? And if you divide that number by 3, you have just a little bit more than 1. So that's a little bit more than 1 radian. 1 radian would be about there. This is pi third radian. Then you take half of that, then you have pi 6 radians. Okay? Good deal. have, remind me?
Stewart. Jake Stewart.
Okay, got it. Jake Stewart. Good. All right. So now we're only missing J.D. Williams, which we haven't seen from the beginning, and Jalen. I think they're the only two we're missing now. All right, good deal. Nope, yeah. All right. All right, any questions then? So get an idea what these radiant measures are and about what they are. Now, you really, I do it, but in terms of degrees, this is 360 degrees, 180 degrees, 90 degrees, 45 degrees, a third of 180 is 60 degrees, 30 degrees, just to get the reference there, okay? The ones we'll be using, all of these will be using a lot, okay? Pi 6, pi 4s, pi 3rds, pi halves, and quite often pi and 2 pi. Those are going to be our favorite angles, okay, to do general stuff with. Of course, in real life, you're going to have all sorts of angles involved with it. But these, if you get these in mind, you get a lot of the key elements and put together. Okay? Any questions? Now, did anyone need that a little longer? Sorry, I didn't mean to go too fast. Anyone need it? Okay. All right. Now, I think I already mentioned this last time. Our Cartesian coordinate system that we have over here, okay, the two axes, horizontal and vertical, split it into 4 quadrants, quarters of the plane, and we number those quadrants 1, 2, 3, and 4. Okay? And that's why we go, because we go or why we go counterclockwise. Now, this is terrible, but I'm really anal retentive about some things. I look over there and I see the projector on, and nobody in the room. Projector bulbs cost money. I got to turn that off. I'll be like that. Out of my budget. They have to replace books. Okay, so we count around that way, and that's why I don't know which was the chicken and which was the egg. Something came first, and that's why we go counterclockwise. So, in other words, angles in the first quadrant, radian measures are from 0 to pi halves radians. Second quadrant from pi halves to pi radians. Third quadrant from pi to 3 halves pi. And fourth quadrant from 3 halves pi to 2 pi. Now, those are the angles, the radian measures in the quadrants. On the boundaries of the quadrants, we call these the quadrantal angles. Okay? 0, pi halves, pi, 3 halves pi. And over here it gets back to 2 pi. 2 pi and 0 are coterminal angles. Same angle, just different names. Okay? Now, we have special names for angles in the first quadrant. Or acute angles. Acute. Okay. No. Okay. Acute angles meaning less than pi halves. If they're in the second quadrant, we also have a name for them. Obtuse angles. Okay? And y'all probably are too young for this, but Did any of you ever see the Shawshank Redemption movie? Huh? Oh, okay. Well, never mind. One of my favorite lines in there is when Tim, whatever his name is, the actor, called the warden. He was in jail for killing his wife, but he didn't kill his wife. And but he's an accountant, and a very good accountant. And he was doing things. Well, someone showed up and doing things for the warden, and the warden's making a lot of money because he's helping, with taxes and things and bookkeeping for him. And the warden was crooked. And someone shows up that actually knew the guy who killed his wife and told the story of it, and that would set him free. But the warden chooses not to because he's making money off of it. So he has the guy killed, the one who knew the other thing. But before that happened, he said, "But sir, this could," he said, "stop being obtuse about this." And he used that term. He got thrown into solitary for like a week or two, because he called the warden obtuse. From then on, I've always remembered obtuse. It's bizarre. I don't know why he used that term. But anyway, obtuse. We don't have special names for them over here, but we can refer to the angles here as negative acute angles and negative obtuse angles. So we could still use the same terms there. Okay? Now, we used this term before. Here, I've used it today. Here it is again. Two angles are coterminal when they have the same initial side, and we always use the same initial side, but also have the same terminal side, but are different angles, like 0 and 2 pi. Same initial side and same terminal side, but they're just two different angles. 0 and 2 pi are that, as are pi 6 and 13/6 pi. 2 pi plus pi 6, well, 2 pi is 12/6 pi, plus another pi, so that would be it. Or even another one, minus 11/6 pi is also coterminal with this. So there's an infinite number of coterminal angles that have exactly the same initial and terminal sides, but just have different names. You can find an angle, and I told you this already last time, but you can find an angle that is coterminal to a given angle theta by simply adding or subtracting one complete revolution to it. Wherever your angle is, this angle here, add 2 pi to it, and you're back at that same place. Or subtract 2 pi from it, and you're back at the same place. So those are your coterminal angles. So wherever you are, add or subtract 2 pi or one revolution, and you're at the same place, but now with a different name. A given angle theta has infinitely many coterminal angles. For example, theta equal pi 6, the one we use right up there, is coterminal with these. Pi 6 plus 2n pi. Yes?
You go to the part where you say any angle add 4 or subtract 2.
Add 2 pi or subtract 2 pi, or any multiple of 2 pi. That gives you coterminal angles. Because 2 pi is one complete revolution. So if this is your angle here, add one complete revolution, you're right back at where you were, but you have a different number now. Okay? So what they're doing here, and it's a little bizarre, if they had written this as 2 pi n, that would make it a little clearer. Or n 2 pi, or any other way, where n is any integer. Not fraction, not decimal, integer. 0, that would be pi 6. 1, that would be 13/6 pi. -1 would be minus 11/6 pi. And just keep adding, doing integers in there, 2, 3, 17, 843, whatever integer you want to put there, add that to this, and you're back at the same place. Any multiple of 2 pi. Where n is any integer. It says n, infinite number of integers, infinite number of coterminal angles. Right? Okay. Here's example 1. Okay. And if you have the book, it's on page 262. Now, here's one example of what I was talking about earlier. And hopefully you'll see this in the ebook as well. But you see here's example 1. Right under there it says, see larsonprecalculus.com, a free website for an interactive version of this type of an example. So it may be exactly like this, or it may have other values to it, but you get to interact with it. And not every example has that, but certain ones in each section, maybe not every section, but most sections will have at least one example that you can go to that site. Okay? larsonprecalculus.com. Free. You don't have to have a code or anything. You just go to it. People who don't own the book can go to it. You know, anyone can go to it. Okay. So, let's do it. For the positive angle 13th pi 6. They should have just said this. Find a coterminal angle with that. What would you do? Add or subtract 2 pi. Which you want to do first? Add. Okay, you want to add 2 pi. Well, how many 6 are 2 pi? 12 6 is 2 pi, right? So 12 over 6 is 2. So that would be 12 6. So add 12 6 to 13 6, and what do you get? 25 pi 6, okay? There's a subtract. Now they say subtract 2, so let's subtract 2 pi. And 2 pi again was 12 6, so subtract that from 13 6, and what you got? Pi over 6, and we already knew that, so pi 6. Well, here is 13 6 pi. Okay, starting with the initial side in the positive x direction. That's your initial side. 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, 7 6, 8 6, 9 6, 10 6, 11 6, 12 6, 13 6 pi. There we are. Or we could subtract 2 pi from that, go back one complete revolution till you get here, and you're at pi over 6. That's how it works. I hate when they give you the example and show you all the answer without letting you think through it. Okay? Most of them, they don't do this, but occasionally like this, they do. Okay? Make sense? Unfortunately, the next one's going to be very similar. Okay? For this negative angle, negative 2/3 pi. How can you find the coterminal angle to that? Add 2 pi to it. And how many thirds is 2 pi? 6 thirds pi, right, okay? So if you add 6/3 pi to negative 2/3 pi, what do you get? 4/3 pi. And that's exactly what they do here. They just do this and pop it up as the answer. I like to change this to thirds, and that would be 6/3 pi, okay? Y'all may not be used to doing your fractions that way, but it makes sense. But if that doesn't make sense, especially when you're dealing with pies, here's a way to make it make sense. Let's imagine that we had 2 pies here. And you split those into thirds. How many thirds of a pie do you have? 6, right? 6/3 pie. 3/3 here, 3/3 there. You have 2 pies to begin with, right? I think in terms of food, I've always had, always will. Okay. Now that's one way. You could have subtracted another 6/3 pi from that and get negative 8/3 pi. There's another coterminal angle that would have gone around that way again. But adding 2 pi to this would have started at this angle and gone all the way around to here. And so negative 2/3 pi plus 6/3 pi would be 4/3 pi. And sure enough, that's 4/3 pi. 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. There it is. Okay. Same place. Negative 2/3 pi, there's negative 1/3 pi, negative 2/3 pi. Got it. Okay, makes sense? All right. Look, if something I'm saying doesn't make sense to you, stop me. Ask questions. It makes sense to me, but that doesn't mean it has to make sense to you. So please don't let me just run my mouth up here. If it's not making sense, say, hey, that isn't making any sense to me. I don't understand what you're saying. I'm not offended. I'll try something else. Okay? All right. Now, a couple more definitions. Two positive angles. Positive angles now. No negative angles, positive. Alpha and beta. They are complementary. In other words, now this is with an E, not an I. Okay? They're complementary, meaning they, what word do you almost see in that? Second? Or? Complete. Yes, they complete or complement each other. And by the way, have you ever wondered why it's called a right angle? The Greeks thought it was the perfect angle. Okay? Guess what? Which wall is going to give you the greatest strength? One that's perpendicular to the floor. If it was leaning that way, it would tend to fall that way. If it's leaning this way, it would tend to fall this way. If it's straight up perpendicular, it's a perfect angle. It's a right angle. It's right. It's perfect. I don't know why they didn't call it left, but that would be more perfect. Never mind. Right? You agree? Jake? Right. Left would be more perfect. Right. I noticed he's writing with his correct hand. Okay. I do too. Okay. So those are complementary, so they complete each other and make a perfect angle or a right angle. That's what complementary angles. The sum, two positive angles whose sum is pi halves. Okay? Now, there's another two angles. They have to be positive too. They are called supplementary or supplements of each other when the sum is pi. So, tell me what types of angles alpha and beta have to be here to be complementary. They got to be positive angles and to be pi halves. Both of them have to be acute angles, exactly, because they add to be 90 pi halves, which is, anything less than that is acute. On these, to be supplementary, what do they have to be? One acute, one obtuse, unless both of them are right angles. Okay. That's the only way you get around from that. So for two angles to be complementary, they both have to be acute. So they've got to be positive, they've got to add to be pi halves. To be supplementary, one of them, if one of them's acute, the other one's got to be obtuse. If one of them's obtuse, the other's got to be acute. But they could be two right angles. Only way around the other. Okay, does that make sense? All right, let's see where we are. All right. Now, they're skipping example 2. So let's us do example 2. If I can find some white space to put it on. Well, I think it'd be better to put it over here. Okay, we'll put it here. The complements of 2/5 pi, or 2 pi over 5. Does that angle have a complement? Second? Okay, we're going to find out. How do we find out? Okay, do what now?
We subtract pi over 2.
Okay, subtract that from pi over 2, right? Because these two numbers here have to add to pi halves, right? Well, okay, in order to do that subtraction, what have we got to have? Common denominators. What would be your common denominator? 10. So how many tenths of a pi is pi halves? 5 pi over 2 minus, and how many tenths of a pi is 2/5 pi? 4 pi over 2. And when you subtract those, what do you get? Oh, where did a 2 come from? You let me get away with that? Okay. Tenths, not halves. Okay. Okay, and when you subtract, what do you get? Pi over 10. Okay, perfect. Okay, the complementary angle to 2/5 pi is pi tenths because they add to be pi halves. Okay? Now, how about the supplementary angle to 2/5 pi? Okay, then you subtract from pi. So it'd be pi minus 2/5 pi. Well, what's your common denominator there? 5, is that what I heard? Yeah, that's what I thought I heard, okay. Right. And what would be, how many fifths of a pi is pi? How many fifths of a pi is pi? 5 pi over 5, because 5 over 5 is 1, right? Do that subtraction, what do you get? Second? 3/5 pi. Okay. So the supplementary angle to 2/5 pi would be 3/5 pi, because they add to be 5/5 pi, which is pi. Perfect. Very good. That was the A part. The B part. What is the complementary angle to 4/5 pi? What's the complementary angle to 4/5 pi? Okay. Okay, you're going to subtract it from, okay, you're going to do 5 pi over 10, which is 2/3 pi, and make this 8 pi over 10, right? Okay. That's pretty ugly, isn't it? Let me see if I can make that look a little better. So that'd be 8/10 pi. And what does that give you? Negative 3/10 pi. Okay? Is that the complementary angle to 4/5 pi?
No,
Why not?
Positive,
Yes, it has to be positive. So it can't be.
so you have to add 5/10.
Okay, okay.
5
What else does it have to be complementary? Acute. And guess what? 4/5 pi is obtuse, so it doesn't have a complementary angle because it's not an acute angle. Okay? So that's why you wind up getting a negative. And you can have a negative complementary angle. The reason is you started with an obtuse, and that's why it was wrong. So there is no complementary angle to 4/5 pi because it's greater than pi halves. But is there a supplementary angle to 4/5 pi? What is it?
So starting off as, what was the original?
Start with pi, which is 5/5 pi. Subtract 4/5 pi from it, and what do you get? 1/5 pi. Pi over 5. All right. Yes, it does have a supplementary angle because it's an obtuse angle, and it has a an acute supplementary angle. Pi/5. See, pi/5 has a complementary angle because it's acute. 4/5 pi is obtuse, so it doesn't have one. Okay, good deal. All right, and another thing, by the way, since we're mentioning these things, I forgot to mention on the first one, after every example in the book, there's something called a checkpoint. The checkpoint is a couple of examples very much like the ones we just did, but they're just different numbers, and you can do those. If you can't do them, guess what you can do? Audio, video solutions for English and Spanish are available at larsonrecalculus.com. So here, every example in the book, I think, has a checkpoint, which has more of the same type, and there you can go to larsonrecalculus.com and get those solutions as well. Okay? And, I mean, not just solutions, audio-video solutions. So you see it, you hear it, and every checkpoint has that. All right, now we're ready for degree measures. Okay? We're probably more used to degrees than we are for radians, but guess what? I'm hoping all of you are going on to calculus, right? Yes, okay? And when you do, you'll find out you just about live with radians. You know, we don't use degrees that much in calculus because it messes up differentiation and integration, all sorts of things, whereas in radians, your angles work nicely, okay? But we're used to using degrees, so we need to know how to do that. So a second way to measure an angle is in degrees. And that's designated by this little symbol, degree symbol, okay? Now a measure of 1 degree, okay, whereas 1 radian was about 57 degrees or something like that. It's not exactly, approximately. That's equivalent to a rotation of 1/360th of a thing around the circle. In fact, you hardly move it off, okay? Now, where does this 360 come from?
A full circle?
Second?
Full circle?
I said that. 4 quadrants, is that what you said? Yeah. Well, yeah, we're used to that. But actually, way, way back, there was an ancient civilization called the Sumerians. They lived in what later became Babylon, and later than that became Iraq, basically. Okay? Today is Iraq, but, you know, not the same boundaries, but somewhere in that area. In the Fertile Crescent, the Tigris-Euphrates Valley, that's where the Sumerians were. And they were pretty sharp people, but they used a base of 6. Why, nobody knows, but they used a base of 6. So 6 times 10 is 60 degrees in a second, 60 seconds in a minute, 60 minutes in an hour, 60 minutes in a degree, 60 seconds in a minute of that. And then 6 times 60 is 360. I don't know how they came up with it, but anyway, they did. So we can blame it on them. Okay? So to measure angles, it's convenient to mark the degrees on the circumference of a circle like this, and often that's called a protractor if it's a semicircle. But here are those favorite angles that we had. Pi sixth is 30 degrees. Pi fourths is 45 degrees. Pi thirds is 60 degrees. Pi halves is 90 degrees. So you can go all the way around here and identify those degrees. And they correspond directly to those favorite of our radian measures too. Pi sixths, pi fourths, pi thirds, and pi halves. Okay? It's 30, 45, 60, 90, 120, and you just add these numbers to 90 and you get these. 30 and 90 is 120, 45 and 90 is 135, 60 and 90 is 150, 90 and 90 is 180. And then just keep adding. 180 to 30 is 210, so you just go all the way around like that. Those are the degrees that we know the most about. We will soon love them, okay? We will be so familiar with them, we'll call them by their first names. You know, in fact, we'll make up nicknames for them, lovable little nicknames for these degrees. And by the way, these are 30 degrees is 1/12 of a whole circle, 360 like I said all the way around. 45 is 1/8. Well, let's start with it. 360, half of 360 is 180, and half of 180 is 90, and half of 90 is 45. A third of 90 is 30, then 60 and 90. A third of 180 is 60, 120, 180, and just on and on and on. I mean, they all have these wonderful relationships as you go around. Now, once we get into trig, you'll learn to love these even more because the trig functions have very definite values for each one of those and fairly easy to remember and deal with. Okay? Get to know them. They will be your friends, okay, all term long. All right. So a full revolution counterclockwise corresponds to 360 degrees. Half a revolution is 180. I just said this. Quarter revolution is 90, and so on and so on. Because 2 pi radians corresponds to 1 complete revolution, and 360 degrees corresponds to 1 complete revolution, you can say that 365 is the same angle measurement as 2 pi radians, right? This is actually a unit. That's not a unit. We just put it there to let you know we're talking about radians. So we can divide both of these by 2 and get 180 is equal to pi radians. That, folks, gives you a ratio that you can use to convert degrees to radians and radians to degrees. Now, they give you these formulas and basically say memorize them. I don't. I hate memorizing anything, okay? So, here's how I suggest that you do. If you're going from degrees to radians, now I do this for every conversion I do. Physics, chemistry, math if there are any, anything that I'm doing conversion, everyday life, I like to do, and some people I think call it a train track method, but I will show you what I like to do. They have this rule here. To convert degrees to radians, you multiply by this. Radians to degree, you multiply by this. I don't like memorizing things like that, okay? Now, here's that same illustration we started today with. They're doing it again, but now they put the degrees in. 1 complete circle is 2 pi radians, 360 degrees. Now they're putting these in. Pi radians, 180 degrees. Pi halves radians, 90 degrees. Pi fourths radians, 45 degrees. Pi third radians, 60 degrees. And pi sixth radians, 30 degrees. Get to know them. Realize them. Think in terms of these. Okay? But let's do the example, which is coming up. Example. Okay, right. One more thing. When no units of angle measurements are specified, in other words, there's not a little degree symbol. There's not the word degree, or even the abbreviation DEG. If you just see a number and you know they're talking about the angle, they're talking about radians. Because radian really is a unit, okay? So if you see theta equal 2, that's not 2 degrees, unless it has a degree symbol, unless it has the word degree after it, or DEG, or something to indicate its degree, it is radian. That's 2 radians. That would be something over here, not something like here. Okay, so don't do this. Now, it's important to think that way, but when you're using your calculators, make sure you're in the right mode. Your calculators usually have degree mode and radian mode, and sometimes have a grad mode. We're not going to be doing those. But you need to be in the right mode. If you're not in the right mode, you can punch away and give me answers, and they're going to be totally wrong. So your calculator said, yeah, this is what you get. Yeah, but you're in the wrong mode. Okay? So be sure to check that. If there is no unit given, you understand that to be radians. All right, here we are, example 3. Now, I'm going to show you how I do it. And theirs is absolutely right. It started off saying converting from degrees to radians. If they just said 135 degrees, okay, and you want to convert that to radians, what you're going to do is multiply it by a conversion factor, okay? And I do this. You're going to radians, okay? This is your conversion factor. I do it when you talk about converting miles to feet, yards to meters, quarts to liters, anything you're converting. This is how I do it. You put what you're given first, then you do times the conversion factor. Now notice I put 2 blanks here. This blank is for numbers. This blank is for units. Equal to some number times this unit. You're going from degrees to radians, so you're trying to get here. Okay? This is how I set up every conversion I ever do. Okay? Now, the next thing I do is put the units in their place. Don't worry about the numbers. put the units in their place. That's on the second blank. Okay? Now you tell me, we're dealing with degrees and radians. You got to put one of them above the line and one below the line. Which you think goes where? Degrees have to go on the bottom, putting radians on top, right? Put the units in their place, okay? And then you ask yourself, how many degrees are equivalent to how many radians? And you know the answer to that, don't you? 180 degrees is equivalent to pi radians. Okay? Go back to this slide. This slide, there it is, right there. 180 degrees is pi radians. That's all you have to remember. 180 degrees is pi radians. You don't have to remember where they go, what they do. Just set up your conversion, put the units in their place, then match the numbers with the units. Okay? And 180 degrees is always pi radians. Notice here your degrees go out. That's why you put it on the bottom. They cancel each other out. And let's see, can we cancel anything here? Just looking at it, I know 5 will go into that. 5 will go into 13 twice. That will be 27. And 5 will go into that. 5 will go into 18 3 times with 3 left over. That will be 36. Well, I know 9 will go into 27 3 times. 9 will go into 36 4 times. Ha! We've got our answer. 3 pi over 4. 3/4 pi radians. Well, let's see if that's right. 135 degrees. This is 90 degrees. And how much further do you have to go to get to 135? 45. There it is. That's 1/4 pi, 2/4 pi, 3/4 pi. Yeah, that's it. 3/4 of a pi. So that's how I do it. Now, if you want to memorize and do the things they do, fine, go for it. That's perfectly fine. But I do all conversions this way. Write down what you start with, numbers and units. Put in your 2 blanks for your conversion factor. Then put a blank and then the unit you're trying to get to. Okay? Always put units in their place to cancel out and wind up where you want it. And then match the numbers with the units. Yes?
Will radians always go over degrees?
What's that again?
Like, let's say we're converting radians to degrees, will radians still be over degrees?
Well, it's whatever will cancel out. We'll do another one to see if that answers your question. Okay? This next one will be very similar. We're starting with, and you want to see how they did it. Remember our answer, 3/4 of a pi. Okay? 3/4 pi. Okay? Let's see how they do. They say do this, and notice they cancel out degrees, and sure enough, they get 3/4 pi radians, or 3 pi over 4 radians. Okay? Now, I'm going to do the next one without putting what they do. 540 degrees. We want to convert that to radians. So I do the same as before, put blank blank equal blank. We're converting to radians. So that's going to be in radians. You tell me what unit goes where. Always put the units in their place. What unit goes where? Radians on top, degrees on the bottom. And how many radians and how many degrees? 2 pi. You could do 2 pi, but it's easier. Pi radians is 180 degrees. Okay? Now you notice the degrees go out. That's what we wanted them to. That's why we put it on the bottom. And I know I can divide out a 10, so I wiped out the zeros there. And I know that 9 will go into 54. How many times? 6 times. And 9 will go into 18 how many times? Twice. Well, I can do again. 2 will go into 2 once. 2 will go into 6. 3 times. That's 3 pi radians. Okay? Well, let's see if that's right. Okay? 540 degrees. Well, I can take 2 pi out of that, because 2 pi is at 360 degrees. So I subtract 360 from 540, and that would give me 180, and that's
Pi.
another pi. So it's 2 pi, and 1 more pi is 3 pi. Yeah, that works. Does it make sense? All right, good deal. So let me show you how they did it. They just used their conversion, which is fine. If you like memorizing what you put over what and that kind of stuff, same way we did, but I just do it from a different perspective. Cancel the unit, get the units where they belong, then match the numbers with units. That way I don't have to remember who goes on top here, you know. It's already done for me. And that sure enough gives you 3 pi radians. Don't forget the pi, okay? It's in there too, okay? Now, guess what? There's a checkpoint, and it has 2 more examples, and the checkpoints are available at larsonfreecalculus.com, audio video solution for those checkpoints. Okay, now, they skip example 4, so let's go back and us do example 4. And this may answer your question that you had a minute ago. Hopefully it will. This time we're converting minus pi halves radians, and we're converting that to degrees. So we multiply by blank blank equal blank degrees. Where do we start? Always put the units in their place. What unit goes where? Degrees go on top now, and radians on the bottom, so you can cancel out the radians and you're left with degrees right where you want them. Okay? Now, match the numbers with the units. How many degrees correspond to how many radians? 180 degrees is the same as pi radians. Absolutely. Now, guess what you can do? Divide out your pi's and divide 2 into 180, and you get 90. So this will be minus 90 degrees. And we knew that, didn't we? If you're minus pi halves radian, you're minus 90 degrees. So you got that. Oh, I put degrees twice, didn't I? Sorry about that. I'll take one of them off. Okay. Does that make sense? Okay. Let's do the next one. 320 degrees. That's pretty hot. Okay, no, that's 320 degrees. I want to get that to radians. Where do I begin? Radian winds up on top in this one. Degrees on the bottom. That's going to make sense, so degrees will cancel out. And then what numbers correspond to those units? Okay, pi radians is the same as 180 degrees. Always match the numbers with the units. And wait a minute. I'm doing the wrong problem. That was the second. Where did I get? Oh, that was in the checkpoint. Sorry about that. I've almost done the checkpoint for you. I didn't mean to. We should have been at 2 radians. I'm sorry. I was doing example 4B and I did checkpoint 3B. Sorry. So 2 radians, and we're trying to get to degrees. And again, we put radians on the bottom in this case, degrees on the top, so they'll wind up in the right place. And then what do we put where?
Oh,
180 degrees is the same as pi radians. Okay? Now, this is going to be a weird one because it comes out being 360 over pi. That's your answer. Now, if you want an actual number, or at least an approximate number, that is a number. But if you want an approximate number in digits, do 360 divided by pi. Most of your calculators have a pi key, and that's something a little bit greater than 3. So the answer is going to be a little bit less than 120. And I believe it comes out 118, 117, or something like that.
You want us to do that on the test?
114. Say again?
You want us to do that on the test?
That's a perfectly good answer to leave it just like that. Okay? But if you choose to, you can. I know how to make conversions, so I'll do it. And if you get the wrong answer, I'll mark it wrong. Okay? All right. I'll be glad to do that for you. No, I'm just kidding. Okay. I'm not happy to mark wrong. I want to grade correct papers. It's so much easier to grade. I don't have to figure out where you made your error. So get everything right here. Otherwise, you lose points because they get mad at you. Okay, never mind. I'm just kidding. Okay. So that's example 4. And I almost did 3 checkpoint, 3B for you. I got it set up. You can go. All right, we've already done that part. Now we move to applications. Sorry, throat's going on me, sorry. This is on top of page 264 if you do have your ebook now. And here is one application, and it goes back from our definition of what a radian is. A radian is the radian ratio of arc length to radius. Remember that. It's the ratio of arc length to radius. That gives you radians. Remember? Radians. Okay? It can be used to measure arc length then. All you have to do is multiply r times theta, and you get arc length. So here's a very practical application. To get arc length for a circle of radius r, a central angle theta intercepts an arc of length s. Here's what s is. S is equal to r theta. Okay. With theta being measured in radians. Guess what? A lot of problems will give you theta in degrees. If you plug that in, you get a wrong answer. Because this formula only works because that works, and this is your definition of what a radian is. So it has to be, theta has to be in radians, where theta is measured in radians. Note if r is equal to 1, then s is equal to theta. Because if r is 1, s is theta. This is a length measured in inches, feet, centimeters, whatever. This is an angle measured in radians, which is no units at all, but the values of the same. Okay? The theta, the measure for your angle in radians is equal to the arc length of whatever unit your radius was. Okay? So here comes example 5. Also on page 264. A circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees. Radius of 4 inches, the arc intercepted by a central angle of 240 degrees. See, this would be 180 degrees, add another 60 to it. Okay, 240 degrees. What would be the length of that sector of the circle? That's not left to right. That portion of the circumference of the circle. How would you do this? You're looking for arc length, S. What is S? R times theta, right? So plug and chug. What's your R? 4. They don't give you inches. It's 4 inches. I like to use units. Times theta. What's your theta?
240.
Okay. Is that going to give you your answer? No! You can't use degrees in that formula. You have to use radians. So don't use 240. Erase that. Forget that. Take that. Whoops. Eraser didn't work. Take that out of the picture here. Okay? First, go back and change your 240 degrees. Change that to radians. How would we do that? Say again? Okay, and how would you do that? Radians where? On top. Degrees on the bottom, so you can cancel them out. That's perfect. And then you match numbers with the units. Pi radians is the same as 180 degrees. Okay? Well, I'll divide out a 10 first. That's go. Oh, I'll wipe out my degrees. They're gone. We're left with radians. That's good. Divide by 10. And then what will go into 24 and 18? Second? 2 will. 2 will go into 24. 12 times. 2 will go into 18. 9 times. Anything go into 12 and 9? 3. 3 will go into 12. 3 will go into 9. 3. So that gives us 4 pi thirds radians. Okay? My writing stinks. Let me get that cleaned up a little bit. That was a 4. And that's what we plug in here. 4 pi over 3 radians. Okay? That gives you 16 pi over 3. And that will be in inches because your radius was in inches. That's going to be your arc length. Now you want an approximate value for that. Pi is just a little bit more than 3, so this will be a little bit more than 16. No, not even 17, I don't think, is it? Where is it? 16.76 inches. Okay, you can do that on the calculator if you really want it. That is a perfectly good answer. However, if you were doing this for someone that was working for you, I said, oh, I want 16 pi thirds inches of fencing here. They're going to say, what? You know, you say 16 3/4 inch, okay, or something like that. Does that make sense? Okay. And, yeah. Okay, say this one more time.
So for there, you also like right here, you also want to leave just like that.
Yeah, you can leave your answer like this, unless it says give your answer to the nearest hundredth of an inch. Then you would plug in what pi is. Yeah. And quite often, they'll give things like this: nearest tenth of an inch, nearest thousandth of an inch, something like that. 3 significant digits, 4 decimal points. If they give that, then take that down. If they don't specify, that's perfectly fine. This is an actual exact answer. The others are all round off. Yeah. So it's up to you. Okay? Good deal. There is a checkpoint there, and LarsonPrecalculus.com has the worked out solution. Okay, another application is dealing with, okay, let's see how they work this problem. Okay, they went through their little formula and did it, and it gave them the right answer, of course, 4/3 pi radians. Multiply that by r of 4 inches, and that gives you 4 times 4/3 pi, which would be approximately 16.76 inches. It's not exact. That one's exact. 16/3 pi is exact. 16.76 inches is close, approximately. Okay. Note that the units for r are determined by the units for r theta, because theta is really a dimensionless quantity. It has no units. Okay? It's a ratio of 2 similar units. So here's another application. The formula for the length of a circular arc can help you analyze motion of a particle moving at constant speed but along a circular path. Now, we talked about 2 different kinds of speeds here. Linear speed is how far it is, how many inches per second, how many miles per hour, how many kilometers per hour, how many millimeters per second, something like that. That is a linear speed. We also talk about angular speed, which is how many degrees per second, how many radians per second. That is an angular speed. One is measuring length per time, the other is measuring angle per time. So consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed v is going to be how far it traveled, the arc length s, divided by the time it took, t. So that's linear speed, s over t. A length over time. And it happens to be an arc length in this if it's going along a circle. Moreover, if theta is an angle in radian measures corresponding to the arc length s, then the angular speed, and this is the lowercase omega, okay? In the Greek alphabet, a capital omega looks like a horseshoe, okay? The lowercase omega looks like a little w without any wings on it. Just as weird as it is in the English language alphabet. Sometimes the lowercase doesn't look anything like the uppercase. So that's the lowercase Greek letter omega of a particle as the rate at which the central angle is changing. Is your angle divided by time. Linear speed is length divided by time. Angular speed is the central angle divided by time, whatever that happens to be. Now, they give you this and leave out the simplest formula you can use to convert these things. Okay? What is S from our earlier slides? What was S? R theta. So instead of S here, if you put R theta, where theta is measured in radians only, so this would be R theta over T. Then this tells you this is R times omega. Why didn't they take two more steps and show you another one that linear speed V is equal to R times angular speed? Such a simple thing, and yet they left you hanging. Okay, so there is another formula you can get out of this. V is equal to R theta. Okay, so here we have a sector of a circle. I've actually used the term incorrectly before, and I'm correcting myself. My knee hurts. Got to sneeze, sorry. Y'all will wake up? Okay, good. Have to do that every now and then. Make sure y'all are not falling off. Okay. Sector of a circle is the region bounded by two radii of the circle and the intercepted arc. So this is a region. This is an arc length. I almost called that a sector before. That's an arc length of a portion of a circle, a portion of the circumference of a circle. The area, or the region here, is called the sector of the circle. It's the pink colored part. Okay? Now, with that in mind, how can we determine the area of that? Well, the area of a sector of a circle, for a circle of radius r, the area A of some sector of the circle with central angle theta, measured in radians only, would be 1/2 r squared theta. Now, they just sort of pop that out of the blue. Let me give you at least one way I think of this. Okay? Let's go back to the previous slide. And doesn't that look a little bit like a triangle? Yeah. It does a little bit. So let's call this the base of the triangle. It's R. Okay? Now the height of that triangle is, oh, good deal, thank you. the height of that triangle, if you approximate that to be the S, okay, that's not a great approximation, but approximate it to be that, which is r theta, then the area of that would be 1/2 the base times the height. The base is r times r theta. That's 1/2 r squared theta. Now, it's not a great approximation, but guess what? It gives you exactly that formula. Okay? 1/2 r times r theta. R times s. Okay? Now, not exactly where it comes from, but at least that's something I use to remember it by. Another thing that I use to remember is the area is always measured in square length units, like centimeters squared, inches squared, square feet, square yards, square miles, something like that. And theta, remember, is in radians, so it has no units. So at least your unit's right. You have to have r squared, and then the theta is just sort of in there. 1/2 r squared theta. Okay? Now, I'm sorry, that was on a page later. We completely ignored example 6 and example 7. Sorry about that. So let's go back and do example 6 and 7. Well, doesn't look like they have any more examples on here. So are we almost out of time? Oh, how sad. Okay, we're going to have to start on example 6 next time. Sorry about that. I run my yap too much. Okay? Let me give you some homework exercises from just a little over a page away. You can do either 7 or 9. This is on page 267. Either 7 or 9. By the way, there's some of you come in late. You may not have seen it. Let me go back. This is for all of your viewing pleasure. I'll go back to where we started today. For those who came in late, there it was. There is your class code for, what you might call it, the WebAssign, Cengage Unlimited. That's the class code you need. Lawson.al space 1139 space 2952. If you type that in, wherever they ask for a class code, that will give you. You'll get some WebAssign problems there. I'm not ever going to require you to turn those in or do them. They're for your benefit. And you have all the WebAssign tutorial help. You have everything out there WebAssign. You also have access to your ebook, everything that you need for the course, as far as I know. Okay? So let's go back to where we left off here. Okay, that was the last slide. We were going to go to this one. Yeah. Okay. Homework exercises. Either 7 or 9. They both have answers in the back, and they are also at calcchat.com for tutorial help and worked out solutions to those odd number exercises. Then do 11. Again, it's at calcchat.com. Do 13. It's at calcchat.com. Do 15, it's at calcchat.com and at calcview.com. Do either 17 or 19 or both. They're both at calcchat.com, 17's at calcview. Do either 21 or 23 or both. They're both at calcchat, but neither one of them are at calcview. Do 25, it's at calcchat. Do 27, it's at calcchat. Do 29, it's at both calcchat and calcview. and do either 31 or 33. They're both at Calc Chat. 33 is at Calc View. Have I gone too far? No. Okay. Do 35 is at Calc Chat and Calc View. Do 37 is at Calc Chat and Calc View. Now, there's a few here that we haven't done any like. Is converting decimals, degrees to radians, only it's using decimals also, which isn't much different at all, okay? But then, that I was thinking that, there's 39 or 41, they're both at Calc Chat, and then 43 or 45, they're both at Calc Chat. But then here's the ones we hadn't done before, okay? It's converting decimal degree form. In other words, they give degrees in minutes, and they want you to get that into decimals. Now, we didn't do anything with minutes, but it's not that hard. You basically use your conversions just like we did before, but if those give you problems and you can't figure it out using Calc Chat, ask me in class and we'll do 47 in class, or 48, either one. Then 49 and 50, they go the other way. They give you a decimal, and they want it in degree, minutes, seconds. So, that one. And then finding arc length, you can do 51. It's at Calc Chat or Calc View. And finding the central angle, that's 53 at Calc Chat. And 55 is at Calc Chat. Stop there, and we will do the rest of those next time. Okay? Good deal. And Dawson, if you have just a second, do you have another class right after this one?
Not till 11:30.
Okay. What time is it now?
11.
Okay. Well, if you have just a minute, I just wanted to ask you a question. How did you get placed in the class? Now, just for my information. Did they tell you? Did you have to go through some?
They just did it based off the ACT score. But I mean, last year I took AP Calculus.
Right. Okay.
So I don't know why they put me in pre-cal.
Okay. I don't either. That's what I'm asking. What kind of criteria did they use? Did they
I
tell
guess they
you?
used the ACT score.
ACT score. Do you mind telling me what you scored?
It was
On the math part?
23.
23. Okay. The reason I'm asking this, one of my math instructors has some students with close to that score in Math 100. And I thought, how in the world did they put them there? They should be in a higher level math. And that's why I wondered, you didn't have to request that they evaluate that or anything else?
Because they were originally putting me in Math 100, but I was like, I said,
So you said,
yeah, because they were looking at my old, they had an ACT score that was lower, so I got them another ACT score that was higher
right.
for math.
And did someone do it as a special case, or did they just do it? That's what I'm asking.
I think they did it based off your, like, the classes you took too, because that's how I got it. Because I'm a freshman, I just came out of high school too.
Yeah.
And, the dean did my
Okay.
schedule, and she said she based it off of my ACT score and the classes you took.
Is that Dr. Davis or who?
No, it's
Dr. Anthony?
Yeah, Dr. Anthony.
Anthony, okay. You see, that's what I'm asking, because these students, these others, you just put them in Math 100 with really good ACT scores. And I'm thinking, how the world, I'm
Yeah,
reporting
I
all
was
this.
the same thing too. That's what calculus last year.
Yeah.